again. So I'm going to say something about these two papers. Well, throughout the talk, you will realize what these two papers are, unless you want to scan them now. So yeah, it's about quantum reference frames, but well, I'm coming from a slightly different perspective. I'm coming from quantum field theory rather than the usual quantum information story into this. So I will tell you the story the way I learned it and the way I think about it. Okay, so I will start therefore with algebraic quantum field theory, which is where I'm from, and then I'll tell you about measurement and QRFs, and this is where I'm trying to go now. All right, so just very basic to get our bearings in this. So, well, at small scales, we all know, I hope, that physics is governed by the laws of quantum mechanics. And here, sort of mathematical tools that one uses are operators on Hilbert spaces, so observables are described using those operators in Hilbert spaces. And more abstractly, the way I personally like to think about it is using some abstract operator algebra, which is just a fancy way of saying, well, operators in a Hilbert space, but I will not tell you which operators in what Hilbert space. And examples are, well, sort of matrix algebras you kind of are familiar with. You know, qubits are just finite dimensional Hilbert spaces. So that kind of covers quantum mechanics, well, for finite dimensional systems. More generally, you want to talk about quantum systems that have infinitely many degrees of freedom. So even if you go to statistical mechanics, quantum statistical mechanics have so many particles that is as well as infinite. So then you already have to deal with infinite dimensional problems. And well, if you want to quantize a field theory, then you have also infinitely many degrees of freedom. So this is where matrices are not good enough. And already Heisenberg, when he was trying to figure that out, started waving hands about infinite dimensional matrices. And he was almost correct, actually. So, I mean, the idea was there. And then the mathematical description came really properly from von Neumann, who, well, essentially invented the mathematics that was relevant for the problem. So the properties of the infinite dimensional algebras to describe observables, say in quantum statistical mechanics or in QFT, are something called Fewster algebras and von Neumann algebras. I'm going to really use them just to give you the words. Okay, so that's quantum. And then, well, algebras are not enough. So in order to talk about experiments and measurement, so for now I'm not going to make that precise yet, but yeah, just to make sense of that, one has to introduce something on top of that, namely states. And again, in a sort of slightly naive picture, when we are talking about just operators on a fixed Hilbert space, then these states are just elements of this Hilbert space. And more generally, if we are talking about these abstract operator algebras, then states are functionals on A, because, well, broadly speaking, states tell us about expectation values of measurements. So being functionals or being maps from A to numbers also makes sense on this level. So this is a sort of broad overview of mathematics that's involved. So now for something completely different. Okay, so well, just to summarize maybe this, there is some sort of notion that quantum mechanics phenomena can be non-local or are non-local because of things like entanglement, which is a property which concerns somehow the whole system. I think maybe to talk about locality and non-locality, one needs a bit more precise framework than this, but yeah, you might have heard or read in various places that, okay, entanglement makes quantum mechanics non-local. So I will make that precise in a minute. Okay. But actually, in order to talk about things local and non-local, I will jump to a different world, which is the world as high velocities and the description of space and time. And actually, in terms of local and non-local, sort of intuitively, we think about these notions when related to space and localizing something somewhere, or localizing something also sometime. So in order to really connect to that, let me tell you a few words about how physics looks at high velocities, close to the velocity of light. So this is governed by special relativity. So that's another main theory at play. And interestingly enough, we're looking about the history of special relativity. This was actually proposed in the response to a problem. So it wasn't just invented from the void when there was no need for that. There was an actual tension between electrodynamics and mechanics. So Newtonian mechanics was not good enough to describe motions of electrons in such a way that would be compatible with electromagnetism. So in a way, special relativity came at the intersection of these two worlds. And one thing which was important in trying to reconcile electrodynamics with mechanics was introducing the notion that light has a finite velocity. So that was somewhat fundamental, and that was not present in either of those theories. So that came as an extra postulate, which actually made then everything work, which is really brilliant. So the most important take-home message from that here is this idea that well, nothing moves faster than light, and also that light moves in a particular way on something called null rays, that I'm going to move to this picture to explain. So space and time are combined to one structure called space-time. So here space is just one dimension, and then we represent events as points in this diagram. So it has some place and some time, every event. And now sort of motion in space and time is described as some paths in this. So for example, if I'm not moving, I'm just standing, then the space coordinate is constant, so that would be a straight line going like that. And if I'm going back and forth across the room, then both space and time are actually changing, so it would look something like this and then that. Okay, now the important rule that the light moves on these null rays, so this is formalized by giving this space-time some extra structure. We're in 2 dimensions, so there is something which describes distances, measures distances in this 2-dimensional space. So we have, let's see if that works at all. We have R2, which is our space-time, and then we have a metric, which here we can just describe as a 2x2 matrix, so 1, -1, and 0 of diagonal. And then directions would be vectors with 2 coordinates, time coordinate and space coordinate. So these arrows here. And then this metric tells us about what type of directions we are looking at. So what types of arrows here. So we can take the let's call it eta. We can take something which corresponds to the length of that vector, and if it is equal to 0, then this vector is null. If it's less than 0, then this vector is space-like. And if it's greater than 0, then this vector is time-like. Okay, so in this picture, this vector is space-like, this vector is time-like, this vector is time-like, and the yellow lines are null. So what Einstein tells us is that light always goes on these yellow lines, and everything else, so massive particles, observers, us, the world, moves within this light cone, so moves from past to future in time-like directions. Hence, things that are space-like to each other, so whatever happens here and happens here, they cannot talk to each other, they are completely independent. So if I measure something in this region, and measure something in this region, these are absolutely independent measurements. So that's the take-home message from special relativity. And this notion of, well, first of all, this sort of classification of directions into space-like, time-like, and null, it's called causal structure, and this principle that things that are space-like separated are independent is called causality. In this language. Okay, so we have that, we have this quantum stuff, and now, as Einstein did with combining electrodynamics with mechanics, now we want to combine these things together, so special relativity and quantum mechanics. And this is where quantum field theory comes in, and again, it wasn't just invented for the fun of it, although it's a lot of fun, but it was actually invented as a solution to the problem, what if we have small particles where quantum mechanical effects are important and that move very fast, that move close to the velocity of light. Okay, and this situation happens in particle accelerators, so quantum field theory is natural sort of framework theory to describe particle collisions, particle physics, what's called high energy physics these days. And yeah, so high velocity, so there is some input from GR, and they're going to take this causality seriously, this whole structure of Minkowski spacetime, notions of past, future, and space-like separations as well. And from quantum mechanics, we want those observables as elements of an operator algebra, so taking this more abstract viewpoint on things, and then states, expectation values, correlations, entanglement, so all the things that are relevant in quantum theory. Okay, so what's the state of the art in quantum field theory? Well, people know perfectly well how to compute things and how to predict the outcomes of experiments like this one. This is CMS detector in CERN. But the mathematical foundations and conceptual foundations are still a bit under construction. So I have my favorite approach, but I think at the moment, you know, whoever does something, then that's the best approach. So yeah, I'm pragmatical. But the one I was brought up in, and my brain is wired this way, it's called algebraic quantum field theory, and this was designed to essentially study the sort of foundational conceptual problems in quantum field theory. And yeah, I know because of Miklos, and probably some, if not all of you, are familiar with the concept. Hi, Miklos. But for those of you who might not, or who would like a reminder, then I'm just going to have this slide. So the framework goes back to Haag and Kastler from the 60s. And the idea is that you take regions of Minkowski spacetime, like the two-dimensional one I drew before, and you assign to each region the algebra of observables that you can measure, observe in that region. Okay. And then if you have a larger region, so have a smaller one inside a larger one, then you want the smaller algebra to be contained in the larger algebra, so you have more observables to measure in the larger region. So you have the structure of inclusions, and you obtain something called a net of algebras. Okay, and then there are some axioms to go with it, and first and foremost is the one of causality. So this is how special relativity gets mixed into the game. So if I have two regions, O1 and O2, which are space-like, so they shouldn't talk to each other, so we don't want them to talk to each other. If I have operators from one region and operators from the other region, they should correspond to things that are independent. So the most basic requirement, sort of first step to talk about independence is to say that the corresponding algebras, corresponding operator algebras commute. So this is the causality axiom. On top of that, one might require some more refined notion like operational independence and so on. But that's a sort of minimal requirement to be in agreement with special relativity. Okay, and then there is another one which has something to do with the dynamics, and it's called the time slice axiom. It essentially says if I know my operators in a thin time slice, then I can evolve them to the future, and I can also guess what happened in the past. So this is a sort of a quantum analogy of initial value problem in field theory and mechanics, that if you have initial data, you can reconstruct solutions. Here I say if I know my observables at a given time slice, so not like a time zero, okay, because this is a bit too singular. You need to have a little interval in time. If I know my operators in an interval of time, then I know what happens everywhere in space-time. Okay, so that's dynamics. And these are the basic ones, and there's more, but let's say this is maybe enough to understand what's going on. People next door are having more fun than we are. Okay, so yeah, maybe we should close the window. I think it's this machine which is creating the heat. I should have dressed differently for this occasion. All right, so that was special relativity with quantum mechanics. Now, aspirationally, the humanity wants to combine quantum mechanics with general relativity too. Okay, this is called quantum gravity, and we don't have it. But we are working on it as the humanity, and hopefully we will get a consensus what it is. But before we get to quantum gravity, I will talk a bit about quantum gravity. We have a sort of intermediate step. So we have some effects from general relativity, which we mix into the game, but we don't go full quantum gravity. So what can we do? So in GR, you can have spacetimes which are slightly more interesting than Minkowski, namely spacetimes that are curved. So there is some interesting geometry to them. For example, black hole spacetimes, that one even has a hole. De Sitter or Friedman-Robertson-Walker, so cosmological spacetimes. So cosmology is a fun area to study these days. So that picture is the CMB radiation, so kind of the farthest we can look into the past of the universe and see what was going on, was the distribution of energy, radiation, temperature, and well, it's a sort of snapshot of the early universe, and we hope maybe that getting a bit more precision in, we might be able to observe some quantum effects. And for that, one needs to be able to describe quantum fields the way we do on Minkowski spacetime, also on such a cosmological background, so a Big Bang spacetime like this one or this there, so that one can compute things. Also, Schwarzschild spacetime describing a black hole. This is relevant for things like Hawking radiation and sort of effects. So yeah, there is a physical motivation to that. Unfortunately, quantum field theory can also work in such settings, so we can construct QFT models on some more interesting backgrounds. And you can use AQFT. If you have already learned AQFT, then this is not going to be wasted. You can reuse everything on curved spacetime, and it's not much more complicated. So the initial effort was worth it. So you still assign algebras to regions, which is not doing well with this. We still assign algebras to regions. We still require the same two axioms, so Einstein causality and time slice. And well, for practical purposes, if we want to construct models, one also uses perturbation theory. So there's the whole thing called perturbative algebraic quantum field theory. And I see my book is already here. so here, for more information, see this book. Or just ask me. Okay, so I think this is more or less enough of the introduction. Are there any questions at this point? It's a bit of a recap. Okay, everybody still with me? Okay, great.
Is there any difference between time slice axiom and just determinism?
Oh, I don't know. I guess, well, okay, so this is a bit, I think this is a bit interpretational issue, because time slice axiom tells you about the evolution of the algebra, the evolution of the operators, right? And then that is, of course, not what you measure in a particular lab at a particular time, right? Because what you measure is what you describe using the algebra and say a state is the expectation values, right? So yes, so you can say it's a bit like, you know what? It's a bit like with a Schrödinger equation and the evolution of the wave function, right? So Schrödinger equation describes the evolution of the wave function deterministically. Right, but that doesn't really tell you what is going to be the outcome of a given experiment. If you had some other outcome at some other time, right? So I think that's the similar situation. So because usually we also have some sort of wave equation in the background, like Klein-Gordon or Dirac equation. And it plays the same role as Schrödinger's equation in quantum mechanics. Does this make sense?
Yeah.
Okay. Yes.
What do you mean by physical models? Because if I open Wald's little book, I'm going to be able to derive the Unruh vacuum, which presumably describes Hawking radiation from a collapsing star. Does that not count?
Kind of. This is a great book. I'm glad you are opening it. But most things in that book, if not all things, are described in terms of free theories. So free scalar field, free Dirac field, which is a good toy model and a good approximation. But if we really want to talk about the world that we can interact with, we actually need interacting theory, because if everything was free theory, there would be nothing happening of interest. We wouldn't even be talking to each other. This would be extremely sad universe. So that's what I mean physical. So actually, corresponding to reality. But the fact that you can do some approximations and simplifications and still compute things is actually quite remarkable. So. Then you have to somehow put that into your model, and then it goes. But I agree with everything that Bob wrote in that book. Anything else? Okay, so let's just move on then. Okay, so we are going to talk about quantum gravity because quantum gravity is an important problem and we have to solve it. I'm a quantum field theorist, so real quantum gravity people don't take me seriously. But there are some things that you can learn about quantum gravity from quantum field theory, and this is how people tried it first. So what people tried, Feynman already tried it. The standard model of particle physics was not done yet, and Feynman was like, yeah, let's quantize gravity, because he didn't know how hopeless it was. The metric is a field. You take a perturbation of that field and treat it as, sort of G background metric perturbation, and you quantize this on this background. You have background G0 and perturbation H, and off we go. And that actually doesn't work the way the people tried it before. So one of the standard tools of quantum field theory is renormalization. The way that people used to do it, when that was first proposed, was not really applicable to gravity. So the term here is power counting non-renormalizable, which means, well, in renormalization you start with something, some expectation values of some observable. You start computing, you realize that you have some issues, some divergences, some problems, you fix them, and then typically you do it in some perturbation setting, so order by order in, say, h bar and the coupling constant. So you do it, then you realize, oh wow, so I fixed this order, I need to compute the next order, and so on and so on. So you have some corrections to the quantity you are trying to compute. Things that are power counting non-renormalizable, it means that as you're correcting, then you have to correct something at each order. So each order in perturbation theory, you get new kinds of corrections that cannot be absorbed into the previous ones. That is less hopeless than you might think. So in the modern view, you can think of quantum gravity in perturbative approach as effective theory, which means that you can compute things up to any given order, but you don't know anything about the convergence of this whole series. Which, by now, we know that this is kind of not that much worse than in other interacting quantum field theories where we also don't know how to sum the whole series. So as we realize that the other things were hopeless, that this becomes slightly less hopeless. So this is a legit way, I think, to think about computations in quantum gravity. And there's another one, which is called asymptotic safety, which essentially says, hey, maybe we are perturbing around the wrong theory. Let's find the right theory, and then the perturbation will make more sense. And these are renormalization group techniques, and there's a bunch of people here, there's a bunch of people there. They're all doing great work on quantum gravity. So these are sorts of quantum field theoretic approaches to quantum gravity, and they are great. And still, apart from technical issues that are there, I'm more interested in conceptual issues. Well, actually, if you don't like any of this, okay, if you want to do something which is more bottom up, then there is also an idea, well, there's a whole bunch of ideas that maybe space-time is actually discrete in the small scale, and there is an approach called causal set, which postulates that the only fundamental structure of space-time is some events, point-like events, and causality relations, which tells you, well, it's essentially like what I wrote there. 2 points are related if that means that their distance is null or time-like. So take away this whole space-time, just have some points and have these relations. This is a causal set. And even on that, you can actually do quantum field theory. So there is something we can say from QFT perspective, even in such a radical approach to quantum gravity. Okay, So things to consider, so conceptual questions that I'm trying to answer as a mathematical physicist. Some of these fun things are actually developed in Euclidean signature. Now, you ask yourself, how is that even possible? Because all that stuff, you know, in Einstein special relativity, this is very non-Euclidean. So Euclidean would be if I replace that -1 by 1. So if I looked at R2 with just the identity matrix as the metric, so around flat space, then with just Euclidean metric. Now that looks very differently, so it doesn't really have the same features, but it turns out, I mean, you can do tricks that go under the name of Wick rotation, so yeah, it's essentially a computational trick. But it's very useful because a lot of these computations here look better in that Euclidean space then. However, of course, in the end, our world is not Euclidean, our world is Lorentzian, so there is the whole question of, well, how to come back from that to the Lorentzian signature, and wouldn't it be better to actually have something which works directly in the Lorentzian signature, because conceptually speaking, this is where, this is where we live. So I like Lorentzian signature. It's more messy, but it's what we have, so we should love it. Background independence. Okay, so if I have things like this, you know, this perturbative setup that I pick a background and quantize the perturbation, it shouldn't be really dependent on how I split my metric into background and perturbation. Again, this applies to all these approaches, and this is something that I have some results on, and this is something that can be approached from sort of a QFT perspective. What I'm going to talk about today are the last two problems. So first is the problem of gauge invariant observables. So there is a huge symmetry in general relativity that one has to deal with. So this is where these quantum reference frames will come in. And as a sort of byproduct of that, almost, is the question of the loss of locality. So QFT, sort of starts as something local. I want to argue that in the end it becomes slightly less local. Okay, so let me pick up on that last point. So before we start anything, I just want to clarify some language which is used in physics, and I just want to distinguish various things that people mean by locality, because there are several, and we want to be talking about the same thing. So one notion of locality, and one sort of situations when you hear physicists saying locality, they actually mean some type of localization. So, for example, that observables should be localized in bounded regions of space-time, like this little double cone. So not something that extends to infinity. So that's localization. Then there is locality in the sense that interactions are happening at a point. Interactions are point localized. So that is actually very particular to particle physics, where interaction Lagrangian is a local function. So that's yet another notion of locality. And finally, my favorite. So when I say locality, I typically mean causality. But for the purpose of this talk, I will try to stick to these more distinguished things. So I will try to say causality. Meaning that observables assigned to space-like separated regions commute. So this is the sort of fundamental one. Okay, so now we break it, because it's already time to do something controversial. Don't tell my community. So the first type of locality, this is actually already broken in vanilla AQFT, the book of Haag. You already have fields that are not localized in just these double counts, but there are things string localized in sort of cones that extend to infinity. Why? Well, QED. No pun intended. So QED is the theory of quantum electrodynamics. So you have electron, and electron cannot be localized in the box. Why? Well, if you had some electromagnetism in the past, there is something called a Gauss law, which means, unless you put your poor electron in a Faraday cage, you just put it in a wooden box, then you take any sphere around that box, you take the integral of the flux, electric flux going out of that sphere, and you will know that there is a charge inside. So no matter how far you go from your poor electron in the box, you will know that there is charge 1 somewhere inside that sphere. That's super non-local. So the way you describe an electron as a particle is one way is to talk about the Dirac string. So this is an electron, and then a string of photons going out like that to infinity. So this is already like this illusion that particles are things, that you can localize in the box. This is just completely broken if you think about long-range interactions. Yes.
Would the flux go to 0 as you went to infinity?
Not necessarily, actually. So because these Coulomb, because this is this 1/r type of interaction, the Coulomb field of an electron has a very long tail. So in fact, if you go all the way to Scry, to the sort of compactification of Minkowski, the infinity, you still sense that. So there is still a remnant of Gauss's law of this Coulomb field far away. So that is actually what makes QED special. And it's related to a thing called the infrared problem. So this long-range character of things. Thank you. Okay, so we broke one. Okay. The second one is actually very easy to break too, because quantum field theory also works for interactions that are non-local. There are technical difficulties, but again, I mentioned this QFT on causal sets, so on discrete structures. There you use interaction which is very non-local. And that's perfectly fine, that's still quantum field theory, that still obeys this last notion of locality as causality. So I broke two.
Can you?
Yes.
I mean, so in what sense are they non-local? I mean, it doesn't allow signaling, presumably.
No, what I mean by non-local, I mean literally, so the interaction, so in quantum field theory, the interaction, for example, could be described by a Lagrangian like this, phi to the 4, which depends on the value of field at a point. So that I mean by local. So now I could do something else. I could do phi of x, phi of y, and some function of x and y. That interaction is non-local because it depends. So you would represent it as this sort of a blob where there is the point x, there is the point y, and there is some function here that describes their interaction. Okay? And here that would be described as a point. So in quantum field theory, you have things like Feynman diagrams, right? So this is a pointwise interaction like this, and this is x, and this is xy, and some blobby blob. This is a non-local interaction. So by interactions being pointwise localized, I literally mean that. It is, you're right, I mean, it is related to the problem of signaling because, there's this, I don't know if you're familiar with the Sorkin impossible measurement problem. So there is a very nice thought experiment by Raphael Sorkin from a long time ago. Sorry, I don't remember the date. But it's been a sort of, for a long time, there's been a problem in quantum field theory, saying that there could be problems with. Actually, let me just draw a picture, because this is a good question, and I want to give this some appropriate response. So Sorkin thought about the following. So I'm going to set a puzzle and then the solution later on in the slide. So here I have Alice, here I have Bob, who is causally separated from Alice, and here I have Charlie, who is not. So there is some intersection here, and then the question is, okay, so C measures A, B measures C, can A signal to B? Okay, and the answer is, well, it depends on the measurement scheme. So Sorkin says, well, impossible measurement is the one where A signals to B. Now, the fact that, well, so we haven't seen it happening, right? So a condition, a sufficient condition to make it impossible for A to signal to B is to say that the coupling within this region, the interaction in this region is point-like, is like the one here rather than the one here. So it is actually related to that problem. And how to link it to the theory of measurement, I will tell you in a few slides. Good, anything else? Okay, so we broke some locality. Okay, so causality is still holding, right? We can also have it even on discrete structures. So I've been working on that too. But it actually, so where can it fail? It fails if we cannot really localize things at all in regions that we can say are space-like to each other. Because the sort of very drastic situation where we cannot even talk about causality is where everything is localized everywhere, okay? And this is kind of expected in situations like quantum gravity, where the observables in quantum gravity are supposed to be diffeomorphisms, so reparameterization invariant, and such observables will be as non-local as it gets. They have to be. They cannot really be different. Again, I'm going to say a bit more about that soon. And therefore, in this situation where, well, everything fails, the natural concept is to talk about relational observables. So we cannot really talk about local observables in any sense anymore, but we can talk about relations between local observables. And these relations themselves could be seen as fundamental objects we study. So that was, for me, the first time I felt like this is a thing to do, that when these relational observables was when I was looking at this problem of observables in perturbative quantum gravity. So this is where I come from. But actually there is an intermediate situation that I only came across recently. It's where, well, forget this diffeomorphism symmetry and quantizing gravity just for a second. And think about just some fixed background which has a large isometry group, so it has a lot of symmetries. Like Minkowski has a lot of symmetries. Time translations, space translations, boosts, it's all symmetries. But here, when you make a measurement, well, you also have to deal with that symmetry. And in this kind of situation, in the quantum regime, one often uses the notion of a quantum reference frame, and the corresponding observables are in that community called relativized observables. So now when I learned about quantum reference frames, now everything is a quantum reference frame to me. So I think all observables are really secretly relativized observables with respect to some quantum reference frame. And this is what I will try to convince you of too. Well, it's good to name things. So I name observables which arise from relations of local observables, semi-local observables, because they are, yeah, kind of local, almost local, not far from local, and fairly decent. So I'm going to tell you more about these guys. Okay, so measurement. I used the word before, and I want to explain a bit more about what I mean by that. So yeah, as I said, quantum reference frames appear in the situation where we want to measure in the presence of symmetries, but what does it mean to measure in quantum field theory? So quantum field theory survived a very long time without a proper measurement scheme. And there are the works of Reinhard Werner, which go in that direction. But I think the sort of proper measurement scheme for AQFT, at least, was only developed very recently by my dear colleagues Chris Fewster and Rainer Fesch in their paper from 2020, very recent. You can see the idea. I'm not them, although we look so much alike, people confuse us all the time, especially with Chris Fewster. But I will pretend to be Chris for a moment, and I will tell you a bit about that. But he would do it better. But he's having a great time in Vienna right now. Okay, so here's a cartoon of measurement. How do we measure things? Well, first of all, I want both the system and the probe to be quantum field theories in a QFT sense. So we have some A, which models the system, and some probe B, which models, B, which models the probe. So they are those nets of operator algebras, and they couple, they talk to each other in a region K. All right? So then what happens? What I can do, so they both obey this time evolution axiom, this time slice axiom. So I can prepare my field in some initial state in the pre-coupling zone in the past. And so in this region, in the far past, A is uncorrelated with B, so we just have a simple tensor product A tensor B. Something happens here, and then in the future we again have a simple tensor product. Okay, so I prepare some state for the probe field, and then something happens, and then I measure in the future. Okay, so again, what I can measure is some observable B from the probe theory in this region. Again, now both things are independent. And now the expectation value of B then tells me something about what happened in the past, because, well, the theory, the uncoupled theory and the coupled theory also obey that dynamical principle. So there is, so whatever observable here corresponds to some induced system observable of that coupled theory in this region K. Now, I can also reverse that. So if I want to measure some particular observable here, I have to figure out what observable B I need to look at in this region. That's a bit less trivial. Okay, so then that is essentially provided, so this protocol of measurement is provided in this paper of Fewster and Fesch, and this sort of protocol corresponds to a measurement scheme of A. So a measurement scheme of A is specified by all these algebras B and A and this coupling here. And they also developed state update rule and the whole machinery to well, interpret that framework. Now, the thing I want you to remember from this picture is this guy. So the coupling is local. The coupling is local, which actually, so here is coming back to Sorkin's puzzle, they have also shown that because the coupling of these two quantum field theories is local, then we avoid this situation because so this region doesn't really talk to that region, so because coupling only happens locally. So if you go through this protocol and you compute the corresponding conditional expectation values for B don't depend on what's happening in A. So the Fewster phase measurement scheme is free from the Sorkin impossible measurement, which in a way is good because yeah, it tells us something about locality in a very non-trivial way. Read that paper, it's great. But yeah, coupling is local and coupling happens in a region, okay? So this region here is something fixed and yeah, the region is somewhere and sometime, which is a problem in a way if our spacetime has a lot of symmetries, because if it has a lot of symmetries, then well, I can always act with those symmetries on my system. So here is a cartoon. So let's say we have Minkowski, where we have time translations and space translations, so we can move the measurement somewhere else. We can take it another time, and that will correspond to acting on this region K with some symmetry and transforming it to a different region, essentially moving that whole measurement protocol around, and that will correspond to transforming this induced observable also by this symmetry. So, of course, you kind of expect that, okay, that things will change under these symmetry transformations, and they change in a covariant way, okay, because both theories are covariant with respect to the background symmetry, so nothing really horrible happens. But then again, you do want to know when and where you measure. You actually need that information to label your measurement schemes because somehow you want to read off the correct numbers. So you need some sort of labels for to fix that symmetry. Okay, so for that, in practice, we use another physical system. Okay, so for this example of Minkowski spacetime, we use rods and clocks. We know that, right? Here are some rods, right? So this actually deals with the translation symmetry in R3. Here is my origin, here are my basis vectors, and Oriel positions are now known to me. That was a reference frame. I have a clock, which also tells me that I have 2 minutes until 5. And that fixes the time. So reference frame is something we always use in all measurements, in all sort of classical situations, and we don't think about it twice. But the world is quantum, right? I mean, okay, maybe it's a belief thing, but I believe it's quantum. So if we want to really think about this fundamentally, then, you know, when we are talking about one quantum system and we want to find these labels for that quantum system, well, using a classical system is kind of cheating and it doesn't really tell us the whole story. Also, was a wonderful talk of Nihiki and Oist, which I heard online. So there's even more arguments why QRF by reference frames should be quantum. But if you accept that, then, well, you have two systems. So you have all that sort of measurement setup, which I will now call AS, a system, and the algebra of the reference frame. So, yeah, just a second. And they are both acted upon with the symmetries, and now you're interested in the space of invariance. Please go ahead.
So
Yes.
if I was in a space-time which lacked symmetries, for example, I didn't have a time like any vector field,
Yes.
I wouldn't need a reference frame to have a measurement scheme?
So then you would use the structure of spacetime, the
Right.
classical structure, to provide you a reference frame indeed. But then my response to it is actually towards the end, what if you want to quantize that spacetime? So fundamentally, if you think about the metric perturbation as a field too, then you always, I think fundamentally all the observables are relational. But sometimes when your background lacks symmetries and can work as a reference frame itself, then you forget about it. But yes, so this is specific to the situation with symmetries. How do we want to organize it with time? Who is sharing?
So, I mean, you can carry on going, and you can carry on giving people opportunity to ask questions. I think that's fine. I mean, we can stop and then...
Okay, so I think, if that's okay with people, I could go for another 25 minutes with questions and then allow 5 more minutes at the end. Does it make sense? You want me to finish earlier?
Yeah, can we do 20 minutes?
Yeah, we can do 20 minutes, 20 plus 10. Okay, great. Okay, so quantum reference frames. So these are not new. I mean, there are various formulations of what a quantum reference frame is, and the names I've learned in the last 2 years are perspectival, perspective neutral, operational, and there are more words. And some of them are very different and some of them are very similar. But I think, it's important to choose one. So I chose the operational one, not just because my colleagues in Europe were working on it, not at all. It was because they had a nice mathematical definition, and I'm a mathematician, at least these days. So here is the operational approach. And so if you ask me what's a quantum reference frame, I'll tell you this. It's a triple of things: a Hilbert space, a positive operator valued measure on some homogeneous space related to your symmetry group, could be the symmetry group itself, strongly continuous unitary representation of G, and a consistency condition relating the two. Okay, so just to break it down a bit. So this sigma is the space of labels. So I'm thinking about time translations as my symmetry. This sigma would be R, and then G would also be R, so H would be trivial. U is the unitary representation of this group of symmetries. And then, G acts on sigma by shifting things around. So you can shift, say, your subset, your Borel subset, your interval, say, on R, using your symmetry, and then evaluate and get an operator, or you can evaluate and then act with this unitary representation and get an operator. So this action by unitaries should be compatible with the action by shifts on the label space. And this is it, essentially. Nothing more to add, but now what we do with it. And here is another example to think about. I like thinking about this example because it's simple, which is translations on R, just a single quantum mechanical particle. So L2 of R is your Hilbert space. Then these shifts are just shifts of the wave function. and then the P of M is given by multiplying your wave function by characteristic functions of intervals. So also harmless. We have the momentum operator that gives us the unitary. And then this consistency condition, if you do your homework, corresponds exactly to the commutation relation between position and momentum. So at least in this simple case, we can see very hands-on that this is the guy we're looking for. Maybe I will skip that because that's a bit of a longer story. It's another example, but we can maybe talk about it later. Let me talk about examples in perturbative and non-perturbative AQFT. There was the motivational example for me and Chris to actually look at it, which was a paper by Chandrasekaran, Longo, Pennington, and Witten from 2023, out of which we knew Longo, who is a famous operator algebraist from Rome. And of course, there was also Witten, which is why everybody else knew that paper. And it's an interesting paper because it talks about an observer in the sitter, and this observer is modeled by a clock, and then through the coupling of that clock to the quantum field on the sitter, somehow there's some magic about types of von Neumann algebras, which is important to people who compute entropies. So physicists were very excited about it. And Chris and I were very excited about it because we thought, oh my God, this looks like a quantum reference frame. And everybody else noticed that too. Yeah, so in response to that, we wrote one of the papers I showed you at the first slide, which is essentially combining this story about measurement in AQFT with quantum reference frames, and then demonstrating that this mechanism described there is actually something much more general and could work also on other interesting curved spacetimes, so Schwarzschild and Schwarzschild exterior Rindler wedge. Okay, then more recently, well, you can use other things as quantum reference frames. You can use other quantum fields. An interesting situation is where you have like a closed subregion with the boundary, say a double cone with the boundary, and then you can use sort of boundary or corner degrees of freedom as your reference. Okay, so you're like, as we are in the room, right, and we use some sort of relation to points on the wall or in the corners to specify where we are. And you see that this is going to work. Actually, I just need 3 corners. 4 is abandoned to tell you where I am in space.
So you're
yes.
assuming that you're doing this in a convex, simply connected spatial region?
Yeah, so we're actually doing it on something like this. We're doing it on a lens.
Okay.
Yeah, yeah. So it's like a double cone, but with the slice. Yeah. I looked at your work with Aldo. Now you can also take this region to infinity and use variables at infinity as a quantum reference frame. So that's still a bit in progress, but very close to completion. And then you can use, well, that story about relational observables in quantum gravity I told you about before. This is also an example. I didn't know it was an example of a quantum reference frame, but it is. So dynamical coordinate fields that are proposed in the paper with Bruletti and Hagen in 2016, they are also, morally speaking, a quantum reference frame, although a particular operational QRF definition is yet to be applied to that setting. Okay, so this is what's going on in my corner. Let's see, so I have 2 examples worked out in more details. So I have this one and this one worked out in more details. What would the audience want to hear? Do you want to hear about the sitter or do you want to see about quantum gravity? This is, I think this is it. Okay.
Please.
Good. There was somebody who spoke. Okay. Okay. So here, just to well explain the terms. So as I said, local observable algebras could be von Neumann algebras in general, and then they're classified in a very nice way. Some of them even better than the others. So the ones that are factors, so they have trivial center. Center is the intersection of algebra and its commutant. Never mind. Those guys come in certain types. So there's type 1, which is essentially quantum mechanics, qubits, finite dimensional stuff. 1 infinity, also quantum mechanics. Type 2, that's quantum statistical mechanics. 2 infinity also, but there are some differences between them. And type 3, which is the nastiest ones of all, is quantum field theory. Why am I being so judgmental? Okay, so this is about the existence of traces, and traces are how people compute entropies, and this is why the whole nervousness comes about, because type 3 is the one where there are no traces at all, so computing entropies is hopeless. You can compute relative entropies, but absolute entropies, no way. Taking a trace, you're doomed. These guys are slightly better, so type 1n and 2.1 have finite trace, so every operator has a trace, so you can have your fun. Now, 1 infinity and 2 infinity, some operators have traces, which is okay, but yeah, you have to be careful. So the magic of that paper of Chandrasekaran, Pennington, Longo, and Witten was to show that if you take type 3 and couple to an observer with a clock, then you have type 2.1. So from hopeless to really, really good.
Why would you want? I mean, so at least some views in sort of thermodynamics, statistical mechanics only want to deal with relative entropies rather than absolute entropy anyway.
Yeah. So I'm perfectly fine with that.
Okay.
So I think for calculation, the motivation was to calculate entropies of black holes. So this kind of stuff where, yeah, you really want to have absolute entropy. So I can see that as a good motivation. But say from AQFT, and it's okay to have relative entropies too. Okay, so that's what I already said. But yeah, so now from the modern viewpoint that I'm now representing is that, well, these operator algebras are not enough anyway, that we should always have the measurement in mind, and the measurement in presence of symmetries actually naturally leads us to a quantum reference frame. And yeah, so we looked at that paper ourselves. So that observer system is, okay, no surprises, quantum reference frame, and measurements are then understood in this Fewster fallacy approach as relativistic local measurements. Actually, local is important in that too. Actually, yeah, just to write by other people. So there was a later paper by the group from, well, mixed by mostly with Philip Hearn from Okinawa, who works on the perspective neutral approach. So that's a different story, but I should mention that too if people are interested. But yeah, that may be a complementary viewpoint. But yeah, so we essentially take these ingredients. Unlike the paper by Chandrasekaran, Pennington, Longo, and Witten, we do not link this to quantum gravity effects or diffeomorphism invariance, actually. We just link it to background symmetries and yeah, the need for a reference frame. There's slightly different applicability of our methods. And another ingredient is thermal properties of the quantum field theory. So our quantum fields have to be seen in the thermal state, so a state of finite temperature, which sort of technical term is KMS. And then if you have that, so if you have a quantum reference frame that corresponds to a clock, you have your QFT in the KMS state, and there's a particularly nice action of time translations in the KMS state, which actually is responsible for that magic of type change, and you get time to infinity. So this you get out of the box if you have a quantum clock and the QFT in the KMS state. Now, interestingly enough, and this is something we observed, or rather my postdoc Dan observed, was that if you want 2-1, which is the favorite type if you want to compute entropies, that actually has something to do with thermal properties of the QRF. So if you, in addition, assume that your quantum reference frame is capable of thermalizing, so to say, with your QFT at the same temperature, right? Then you actually get type 2-1. And I think this is maybe a new piece of information, and for interpretational reason, a nice way of getting from here to here, which goes beyond just a particular example. Okay, so that was our take on that paper. Here is a picture for those of you technically inclined who really want to see it. But I just want to talk around that picture a bit, because the thing is that the mathematics used there isn't actually very old and somewhat general. So one can describe any decent quantum reference frame by some sort of compression of standard quantum reference frame that you build directly from essentially the data coming from your group in sort of almost canonical way, and then you compress it back to your original situation by some choice of a projection. And yeah, I think in this original paper of Chandrasekharan, Pennington, Long, and Witten, they don't really explain that bit that much, but it's a very general mathematical fact, and I think this sort of construction is actually universal in a way. I can talk about this diagram later if there are some more technical questions. Okay, so let me just spend the last 3 minutes sketching the final example here, which actually addresses your question. So what do we do if we don't have any symmetries at spacetime? And yeah, let me start with a question. General relativity, what is the point? Yeah, I like asking that question in many contexts, but here there is an answer. So actually there is no point. And this is part of the beauty of general relativity, that there is no point. So points in manifolds as mathematical objects, they're great, but there's absolutely no physical meaning to those labels. So something like specifying the coupling zone on spacetime, like I did here, right? This can be done mathematically as, you know, we have point X and point Y and whatever, but that's not physical. There are no labels stuck into the universe that tell us which point is which. So GR is pointless. And the analog of this pointlessness of GR is actually a background with symmetries. So that's a smaller symmetry group than all diffeomorphisms, but it's a similar phenomenon going on. Okay, so if we take quantum gravity seriously, then, you know, in all cases, the true symmetry group that we should be thinking about is the diffeomorphism group. Okay, and hence really the quantum reference frame we need, or the reference frame we need, is that for this whole diffeomorphism. So if we do take that seriously, then all observables are secretly relational, but we might not notice it because, well, sort of in classical physics, right, if we measure things in the lab using the lab equipment, we don't think about the lab equipment as part of the dynamics. But in GR, it is part of the dynamics because, you know, space-time influences matter, matter influences space-time, so we cannot really take these degrees of freedom at the system, these degrees of freedom to what we are measuring. But when we do that, then we build up sort of reference frame and system kind of distinction, and then what we measure is really the relations. So everything is relational. Okay, and I think this is a good way to finish. There are some more technical details if people ask. Thank you very much.